Hey there, and welcome. Today, we're going to break down two really key ideas in algebra, domain and range. Now, I know they might sound a little mathy and formal, but stick with me, because you're about to see they're a surprisingly simple and powerful way to understand how functions really work.
So, let's just start with a kind of a weird question. Can a math function be picky? You know, like a fussy eater? Well, the short answer is yes, absolutely. And believe it or not, understanding that pickiness is the whole key to everything we're talking about today.
I want you to imagine our function is this machine. You put something in one side, we'll call that the input, the machine does its thing, and then something new comes out the other side. That's the output. Simple enough, right? But just like any real machine, you can't just shove whatever you want into it. There are rules you gotta follow, or you're gonna break it.
And of course, those rules have special names in math. This is where we get to our main event, domain and range. Honestly, they're just fancy words for what the machine is allowed to take in and what it's capable of spitting out.
Okay, first up, the domain. The domain is literally just the complete list of all the possible numbers you're allowed to put into your function machine. Think of it as the official list of approved ingredients. Any input that's not on this list, nope, the machine just rejects it.
So if the domain is everything that can go in, you can probably guess what the range is. It's everything that can possibly come out. The range is the complete set of all the potential results or outputs the machine can create after it does its job. It's the full catalog of its finished products. Now, trying to list out every single number in a set can be, well, impossible, especially when you're dealing with infinite stretches of numbers. So mathematicians, being clever, came up with a kind of shorthand, a special language to describe these sets really efficiently, and it's called interval notation. And here's the cheat sheet for that shorthand. The key is actually super simple. Parentheses, the round ones, mean the endpoint is not included. Think of it like an open gate you can get really close to but not stand on. The square brackets mean the endpoint is included, like a closed fence post that's part of the property. Oh, and since you can never actually reach infinity, it always gets a parentheses.
All right, enough with the definitions. Let's be real, the absolute best way to get a feel for domain and range is to just see them. When you've got a graph of a function, you can often find what you need just by looking at the picture.
And this visual is just brilliant. Here's the trick. To find the domain, imagine taking that entire blue line and squashing it flat onto the horizontal x-axis. The mark it leaves? That's your domain. For the range, you do the exact same thing, but you squash it sideways onto the vertical y-axis. That shadow it leaves is your range.
Okay, let's put this into practice. Here's a new graph. Using that squashing or shadow method, I want you to take a look and see if you can figure this one out.
It's your turn. Go ahead and use that squashing method. Pause for a second if you need to. See if you can figure out the domain, that's the horizontal spread, and the range, the vertical spread, of this function.
So, did you get it? Let's break it down. For the domain, we look from left to right. The graph starts just after x equals -3. See that open circle? That means we use a parenthesis. It travels all the way to x equals 1, where there's a solid dot, so we use a square bracket. For the range, we look from bottom to top. The lowest point is y equals -4, and that's a solid dot, so we include it. The highest point is y equals 0, but that point is an open circle, meaning the graph gets infinitely close to 0, but never quite touches it. So we don't include it.
Okay, looking at a picture is great, but what happens when we only have the equation? Well, in that case, we have to read the machine's instruction manual. And it turns out there are basically two huge safety warnings we need to look out for that tell us which inputs are absolutely forbidden.
Rule number 1 is the cardinal sin of arithmetic. You can not, ever, under any circumstances, divide by 0. If you try, our function machine will just completely short-circuit. It's a non-negotiable, fundamental rule of the universe.
So, let's look at an example. Take a function like this one. The second you see that your input variable, x, is sitting in the denominator, the bottom part of a fraction, that's a huge red flag. We have to find any value for x that could possibly make that entire bottom part turn into 0, because that's the one thing that will break our machine.
And finding that forbidden value is pretty easy. We just take the whole denominator, in this case x minus 2, we set it equal to 0, and we solve for x. A little bit of algebra, and we find that if x equals 2, we get division by 0. That means the number 2 is banned. It is officially excluded from the domain. The machine can take any other number in the universe, just not 2.
All right, the second major rule involves square roots. Here in the world of real numbers, we just can't take the square root of a negative number. Our machine, it just doesn't know what to do with that. It's not a valid raw material for the process.
So if you're looking at a function and you see a square root symbol, like this one, another red flag should immediately go up. Our job is to make sure that the stuff inside that square root symbol, it's called the radicand, by the way, we have to make sure it never ever becomes negative.
So how do we do that? Simple. We take the entire expression from inside the root, for this one it's 7 minus x, and we set up a little inequality. We say that this expression must be greater than or equal to 0. 0 is fine, positive numbers are fine, just not negative. And then we just solve that inequality, and it will tell us exactly which x values are safe to put into the machine.
So why does any of this actually matter, right? This isn't just about abstract rules for a math class. Domain and range pop up all the time in the real world, and they give really important context and limits to the data we see every single day.
Take a look at this. This isn't just some random curve I drew. This is real data. It plots the amount of crude oil produced in Alaska every single day, over a period of many, many years. So what can our new friends, domain and range, tell us about this situation?
Let's start with the domain. Remember, that's all the valid inputs, which we plot along the horizontal x-axis. So what does that horizontal spread actually mean in the context of this real-world story about oil production?
And there you have it. The domain isn't just a set of numbers. It's the time frame of our data. It tells us that this information starts around the year 1973 and it ends around 2008. The domain gives our data its historical context, and the range, by the way, would tell us the lowest and highest production levels they ever hit during that time.
So when you boil it all down, this idea of inputs, rules, and outputs is literally everywhere. Think about the domain of temperatures your oven can operate at, or the range of speeds your car can travel. Just think about it for a minute. What are the inputs and outputs, the domains and ranges, of all the different systems that you interact with every single day?